who don't know me, my name is Goldstein. I'm going to be lecturing about a relatively confined topic. It says advanced general relativity on the timetable, but I'm just going to be talking about something called differential forms. Right now, differential forms are very useful for a variety of applications in physics. And for what I'm hoping to reach at the end of this series of lectures are something called the Einstein-Cartan equations. Okay, which provide a very useful way of calculating things in general relativity. But differential forms also the natural language to talk about gauge fields and give a nice way to generalize Stokes' theorem to any number of dimensions. So they're very useful in physics, and very often in people's undergraduate education you don't actually see differential forms. How many of you have seen them in undergrad, or any of you? Okay, some people have seen them. Good. But most of you will not have seen them, so I'm going to start off with a very introductory lecture. Just telling you a little bit about, most of you have probably seen tensors before, but I'm going to be looking at tensors from a particular perspective. So I'll introduce tensors, and then I'll introduce differential forms and some properties of differential forms. Good. So just some conventions. We're going to be using the Einstein summation convention. Okay, that's the Einstein summation convention is if I have repeated indices, I'm going to be implicitly summing over them. So I'll write something like that. AI, BI, that is shorthand for A1, B1, plus A2, B2, plus A3, B3. Hopefully some of you have seen the Einstein summation convention before. For those of you busily taking notes, I will at least make notes available for my first lecture, probably this afternoon when you go through the tutorial, so you don't need to take down everything I say. Good. So in the bench I'm going to be using is very common. So Roman will be spatial indices. So here are the Roman letters, and the sum goes over the spatial indices, and Greek letters will go over the space-time. So if I have repeated Greek indices, I'll also include a sum over a time coordinate. Right, so I'm just going to, the first part of the lecture, I'll just give a brief discussion of tensors, just to get everybody on the same page, and just to give you a perspective on tensors, or a way of thinking about tensors which may be different from how you've thought about them in courses before. Okay, so we're going to start off with just vectors, and I'm going to use a very old-fashioned definition of vectors. The rest of my definition of tensors is more modern, but I'm just going to talk about vectors in the same way you probably learned about them in high school, hopefully. And we're going to think about vectors just about, vectors are a generalization of the concept of displacements. And once again, in this lecture I'm just going to talk about special relativity, and on the next lecture I'll generalize things to curved manifolds and curvature. Good. So vectors are anything which transform in the same way that the displacement does. So let's say I have a vector which has some components, and I perform some coordinate transformation, and it it goes to some new vector which has different components. Okay, so I'm going from some coordinates x, some vector, okay. Right, so, sorry, this is the, I have some coordinate transformation. Hopefully you've seen something like that before. And then the displacements, if I want to know how an infinitesimal displacement transforms, so if I have an infinitesimal displacement dxi, just using the chain rule, that's going to be equal to dxi dxj. So that's now, the bar is just to denote that I've got a new coordinate system, and dx. If anybody doesn't understand anything I say, please interrupt me at any point. Everybody happy so far? Right, and I'm going to use some shorthand. I'm going to refer to this matrix, which tells me how to go from one displacement to another displacement as lambda I j. And that notation is meant to remind you of Lorentz transformations in special relativity, which are a special case of these general coordinate transformations. Good. So that's how, so a vector will be anything which transforms like that. So if I have some vector which has some components AI, that's going to be related to the components in a different coordinate system by that matrix now. Right, so that's how vectors transform. Now, we think of the vector as something independent of the coordinate system. So it shouldn't matter whether I use any particular coordinate system, what the components of my vector is. Let's say I have a particular set of basis vectors. I will write my vector like that. So that's the components of the vector, and those are the basis vectors in a particular coordinate system. And I've told you how these components transform, but I'd like to know how the basis vectors transform. The basis vectors don't transform in exactly the same way, because this object, the vector, shouldn't depend on what basis vectors I use. It should be independent of that. Okay, so this is going to be, whether I write it, that should be equal to the same thing, whether I have it in the barred or the unbarred coordinate system. Right, so in order to work out, the only thing I know is how the components of vectors transform. I can reverse the argument that I just gave. So if I want to go from the barred to the unbarred coordinate system, I get that is the transformation I use, just exchanging the I and ij's. Good. So I can write this as lambda I bar j aj e I bar. Good. And I'd like to compare these things, so I'm going to do something that people often do. And the nice thing about Einstein summation convention is going to relabel my indices, which is not going to affect anything. I'm actually going to call that index, let me call that index j, j bar, and then we call this unbarred I. Okay. Then I can compare this side of the equation and that side of the equation. I can factorize out the AI. So I get 0 is equal to AI, EI plus lambda j bar I ej. Right. Sorry, there's a minus sign there. Okay. Good. Now this is some arbitrary vector AI. This should be true for any vector. So in particular, let's say it should be true for the vector A equal to 1, 0, 0. So if I choose that vector, I pick out I equals 1 in this equation. Similarly, I could choose the vector where it has 0, 1, 0, and then I would pick I equals 2, or I could pick out 0, 0, 1, and then I would pick out the equation where I have I equals 3. So this should be true for any I. And so in summary, a vector transforms like this. Sorry. Okay. I'm trying to jump ahead of myself. So that's how a vector transforms, and that's how the components of the vector transforms, and the basis vectors transform as okay. So let me just point out. So this is sort of a scalar equation. This relates the components of the scalar components of one vector to another. This is actually a vector equation. This relates one vector to a sum of other vectors. All right. Hopefully, many of you have seen something like this before. Good. So that's vectors. And once we have vectors and the transformation properties of vectors, we can define any tensors we like. So the first tensor I'm going to define are tensors called one forms. And in this perspective, from the perspective I'm going to talk about in this lecture, I'm going to think of one forms not maybe the way you thought of them before, but I'm just going to think of one forms as linear maps. Okay. So I'll write a one form like this, and I write it with an empty space there. That's because it's a map which takes something, and it's a linear map which maps vectors to numbers. So what happens is I have a one form, I feed a vector to the one form, and that gives me a number. It's a map, and the important thing about it is it's a linear map. So let's say, so we can immediately, the fact that it's linear immediately tells us a lot about it. So I can take my vector and write it in terms of a particular basis. So my vector will be like that. And because this is a linear map, property of a linear map is I can take out that AI. So this is going to be equal to AI p tilde, that's the one form acting on the basis vector. And I'm going to give this a special name when I feed one of my basis vectors to the one form. I'm going to give this a special name. I'm going to call that PI. Okay, this is a definition of what PI is. So what I get when I feed a particular basis vector to my one form. And that gives you the normal expression, although I introduced this using more modern language, that just gives this P acting on A, is just basically the dot product between the one form P and the vector A, sorry. Summing over the special components A. Everybody happy? Yeah, question?
That PI, is that what's known as dual vector? Sorry?
Yeah. Well, I'm calling it a one form. Other people call it a dual vector or a covector. Yeah. It's the same thing. It's a dual vector is exactly what people say. What people call a dual vector is actually this. It's a linear map which takes a vector to a number. Good. So we've introduced, I've got, in a particular coordinate system, I've got some basis vectors. And I'm also going to now define basis one forms. And I'm going to use some suggested notation for them. Right, so basis one forms. So I'm going to write my basis one forms like this. It's got a tilde to denote that it's a one form, and it's it's going to eat a vector and give me a number, so I put a bracket like that. So this is actually a one form, it's not like the differential of x. It's a one form, that's why I've drawn a tilde to differentiate it. And the way I define my basis one forms is that if I give them one of my basis vectors, so they're sort of orthogonal to the basis vectors, if I give them a basis vector, I get a Conan-Decker delta. So my basis one forms are defined by that formula. So in terms of language of other people, these will be the dual basis. What do people say? The canonical dual basis. But I take my, it's the one form, if I feed it my basis vectors, it gives me a Conan-Decker delta. And since it's a basis, I can write any particular, I can write any one form in terms of this basis, and any one form in terms of this basis will be written like that. Okay, you can check that. Do you want me to show you now that this gives me the same expression as that? Or is everybody happy? Shall I just prove that quickly for you? Who wants me to prove it? Okay. So, this object, pi dxi, acting on the vector A, so that's going to be equal to pi delta xi ai. Sorry, let me just use a different summation index. And because this is linear map, I can take that out. So it's pi aj delta tilde xi acting on ej. Then this is nothing but the Conan-Decker delta ij, and so that collapses the sum, and I'm once again left with pi. Okay, so that shows you how this is a good way, a good basis for the one forms. Right, so now I can define, I've defined one forms, I can define tensors. I have a general tensor, and I'm going to talk about n m tensors. Can anybody guess what an n m tensor does, if you don't know already? You might not know what the n and the m stand for. Okay, so an n m tensor will take m vectors and n one forms and give you a number. So also it's a linear map. It's a linear map from m vectors and n one forms and that gives you a number. And the components of a tensor, so a tensor will have n upper indices and m lower indices. So I'll write it like a1 up to an, b1, bm. And if I want to know what the components of that tensor is, I just feed the tensor my basis vectors. That's going to be t of dx1, that should be a tilde, that's dx an, and I feed it e1, yeah, that's what the component of that tensor is. And I think this afternoon, given everything I've told you, you can check that this tells you how tensors transform. So, in the GR course that I teach, the introductory GR course I teach here, I don't introduce tensors like this, I just introduce tensors in terms of their transformation properties. But the way I've defined tensors now implies they have the following transformation properties. So T A1 to AN. Okay, so let's say I'm in some new coordinate system, B1 up to Bn, and that's going to be lambda A1 C1 dot dot. And I have a lambda, it's D1 bar, let's say D1, and that will be T C1 dot dot. Okay, so some of you may have seen that definition of tensors before. But basically, because of this linearity property, once I know how vectors transform, and I know how basis vectors transform, that implies this transformation property for all tensors. And finally, let me introduce some more notation. And there's a way of multiplying tensors together, and it has the incredibly unimaginative name of the tensor product. And I'll just define the tensor product for one forms, but hopefully you'll be able to work out how you can generalize the tensor product to more general tensors. So, yeah.
Can you please disregard that part?
Sorry?
Can you say again about that part?
About this part?
Yeah.
Okay, so people sometimes define tensors as objects which transform in this way. In the same way that I define vectors as I said a vector is something which has components which transform in this way. Sometimes people will define, say, a tensor is something whose components transform in this way. What you can check this afternoon in the tutorial session is just starting with this transformation law for vectors and the fact that tensors are linear maps on vectors and one forms, that'll imply this transformation law for tensors. Okay. Any other questions?
And indexing, I mean, was one and...
Okay, I've just, you mean over here?
Yeah, and then we'll see them.
So this object has n upper indices, n upper indices and m lower indices. For each index, I'm going to have one of these transformation matrices. So for these n indices, I've got a matrix like that, which has a barred upper index, an unbarred lower index, and that is summed with the upper index of this tensor. So these upper indices here. For each lower index, I've got a matrix like this, which has a barred lower index, an unbarred upper index, and that sums over all the lower indices. Okay. But maybe in the tutorial this afternoon we can go through that in more detail. I don't want to dwell on it too much because for people who've seen this already it's kind of boring. For people who haven't seen it already, we can go over the details in the tutorial. Good. So there's a way of multiplying tensors, which is unimaginatively called the tensor product. So I'm going to show you the definition, which I take two one forms. So I'm going to multiply two one forms, and people use this to differentiate from the normal product. Put a circle around it to show that we're not talking about the normal product. So the tensor product for one forms will take two one forms, and I'll map it to something which is a 0-2 tensor. So this will take two objects. That each of these objects, I feed them a vector. It's going to give me a number, and that's the tensor product gives me a new object. When I feed it two vectors, it's going to give me a number. So So here I've taken the tensor product of two one forms. This is a 0-2 tensor. So I have to feed it two vectors. So I feed this object two vectors, and we call them A and B. And the definition of the tensor product is that this is equal to the one form P acting on A, and now this is just the normal product, Q acting on B. And that defines for us the tensor product, or a way of multiplying tensors to get new higher order tensors. Any questions about the tensor product? Yeah?
That's a twofold, right?
This is not a two-form. This is a 0-2 tensor. I'll define two forms in a little bit. Okay, two forms are special 0-2 tensors. And we'll see in a little bit what the distinction is.
Sorry.
Yeah.
So the tensor product, the definition,
Yeah.
it can be directly used to verify this transformation property as well.
No, it's consistent with the transformation property, and once you understand the tensor product, then you can understand. Let me rather say, I can write a particular tensor in terms of tensor products of my basis vectors, and that'll give you a nice way of understanding this transformation property. So let me I'll sort of semi-answer that question. So for a 0-2 tensor, I can write my basis 1 forms. I can write my basis 1 forms as the tensor product of the basis 1 forms for. I can write the basis of a 0-2 tensor. I can write as a tensor product of the basis 1 forms. And then, if you know how these objects transform, it's very easy to see how this object transforms. Yeah, but maybe we can chat more about that this afternoon. Okay, so just some more notation. When I'm going to define the anti-symmetrization over particular indices like this. Some people define this without a factor of a half. On a different day, I might also define it without a factor of a half, but today I'm defining it with a factor of a half. So this is equal to the anti-symmetric QB minus B beta Q alpha. Okay, and there's also one can define the symmetrization over two indices, which use round brackets, and then that has a plus sign. Good. So now I can start talking about differential forms now that I've reviewed tensors. So one forms are really special. Because they can, in addition to being something which allows us to map vectors to numbers, we can also use them to map. I can use them to map a line to a number, not just a vector at one point in space, but I can take some line and map it to a number. So let's see how that works. Let's say I have some line which goes from a point A to a point B. And this line, let's say, is parameterized in terms of some parameter u. Okay, so this is just some parametric curve that I've defined in space. And this curve is going to have a tangent vector, and the components of the tangent vector are just the derivatives with respect to u. So that's the tangent. Okay, so at any point of the curve, I've got some, okay, that's not a very well drawn tangent, but you get the idea. Some tangent vector. And if we shift, okay, sorry, that, for those of you who can't see, that's a capital U as opposed to that parameter U. Please don't get confused. Good, so if we shift our parameter u by some infinitesimal amount, then we get an infinitesimal displacement along the curve. Okay, and we can think of some infinitesimal displacement vector which points along the curve. And so the displacement in the xi direction, just from the chain rule, is going to be equal to dxi by u du. Okay, and this is nothing but my tangent vector, the component of my tangent vector, ui, capital Ui, lowercase u. And so this will be the components of my infinitesimal displacement vector. So I'll write that my infinitesimal displacement vector is, it has these components in the ith direction, and it's a vector, so I'll write everything in terms of some particular basis. Everybody happy? Good, so what I'm going to do in order to map this curve to a number is, I'm going to I can divide up this curve into a whole lot of little dLs. And I want to take a one form and map this one form is going to map this whole line to a number. Okay, so let's say I've got a one form P, and okay, let me just consider I'll consider a finite non-infinitesimal displacement, so delta L, and then this is going to be delta U. So that's one of these little line segments, and then I'm going to act on that. So I'm going to feed that vector to my one form, and as we've discussed, that's going to give us a number, and the number is just going to be P contracted with that. So that's going to be equal to Ui Pi delta U, and so in terms of these little infinitesimal, these are not in terms of these finite displacements, that'll be Pi some delta xi, so delta U. Okay, then I can take all these numbers and just add them up, and that'll give me some sum. So I can sum up these along my curve. I can sum up these delta L's, and then I'm going to take the limit as delta L goes to 0. So instead of finite displacements, I get infinitesimal displacements. And this should remind you of how one defines integrals. And I'm going to write this integral as the integral of my one form. Let me call this curve C1. And to denote the fact that I'm integrating along C1, I'll write it like that. So that looks very neat and compact. And let me just write out exactly what that means. Good. So what that is equal to is this one. I have to think of this one form as acting on this infinitesimal length element. So that's P acting on dl, and that'll be the integral from a to b of pi dxi du du. And way I would write my normal line element. Okay, so this is just a very compact way of writing a line element. And the reason I don't have a little differential in there is I'm implicitly thinking of this, this one form acting on this little vector as I move along the curve. Any questions? Good. So just some a quick comment. So everything I said here can be easily generalized from space. I was just talking about 3 dimensions. This can easily be generalized to space-time. Everywhere you see an I, you just put a Greek index, and then the summation goes over the space-time indices. And so this looks like a lot of work. Okay, so I can also, this is, in terms of my original notation, this, I would write this as P I dx I. Okay, so all this work that I've done on the board, seems like I've done a lot of work just to erase this little tilde, to go from one form to the old way that you used to write a line integral. But as you'll see, all this work is going to end up being worth it, because this gives us a good way to generalize line integrals, integrals over surfaces, integrals over volumes, and in the end it's going to give us a very nice way of thinking about Stokes' theorem in any number of dimensions, rather than having to learn all those different formulas and different forms of Stokes' theorem. Yeah, question?
So we said that one form can map a line to a number.
Yeah.
So we did that by integrating, we collect all of the tangent vector by acting with the one form.
Yeah.
So can we also act on the surface and collect all of the tangents?
Yeah, fantastic. So you've anticipated the next section, which is 2 forms. So that'll show you how to take an infinitesimal area element, which we can think of as the cross product of 2 vectors, and to act on that with the 2 form. That's going to give us a number, and we'll see how we can use 2 forms to map an area to a number.
So the one form doesn't do that. I mean,
no, the one form is maps lines to numbers. Okay, and we're going to have to for an n-dimensional surface, you're going to have to use an n form to map that surface to a number. Good. Let's not get quite too far ahead of ourselves. Let's talk about 2 forms. And now we'll also see why 2 forms are not exactly the same as 0-2 tensors. Okay, so 2 forms, we're going to map areas or surfaces, 2D surfaces, to a number. And so let's say I have some surface or some 2-dimensional volume, which I'm going to call C2, and I'm going to use very similar notation. So I'm going to have the integral over C2, and now instead of a 1 form, I'm going to have something called a 2 form. And so I don't get confused, and I know there's a 2 form, people will often put a 2 with brackets in there, tell us that we're dealing with a 2 form, and that integral is going to be equal to a number. And so that's what we want, and let's see how we have to go about it. So just like we had that infinitesimal tangent vector, we're going to have to define an infinitesimal volume. Now let's say I give you 2 vectors, let me call them V and W. Those 2 vectors define, you can think of them as defining a parabola which has some area. Okay, can anybody, in terms of those vectors, does anybody know what the area of that parabola is?
it's a magnitude of the cross product.
Okay, so it's equal to, so this area, so let me call that A. So that's equal to the magnitude of V cross B, and it's very easy to see that. So let me divide this that parabola up into two triangles. The magnitude of V cross B, as you should remember, is VW sine theta. Theta is that angle. So this will be, that length will be W, that height there will be V sine theta. The area of a triangle is half base times the height. So the area of this triangle will be a half VW sine theta, and the area of the whole parallelogram will be VW sine theta. And I should put an absolute value sign in case sine theta is more than 90 degrees. Okay, any questions about that? Everybody happy with that? Right, so those, that's the area which I get from the cross product. So, all right, plus or minus the area is equal to V times W. And now I'm just going to think of two-dimensional vectors. We can easily generalize that to higher dimensional vectors. So the components of the curl of VW is Vx Wy minus Ey. So that's just the curl of those two vectors, and I can write this in a nice way. I can, out of these two vectors, I can make a matrix. The first column is the first vector, the second column is the second vector, and I take the determinant of that vector, so I can write this as x VW, with the understanding that by this notation I mean I take the vector V, I make that the first column of my matrix, I take the vector W, I make that the second column of my matrix. Okay. So a general 0-2 tensor will map any two vectors to a number. Well, you know, a 0-2 tensor is something maps two vectors to a number. But now I want to construct a special 0-2 tensor. I want to construct a special 0-2 tensor that when I give it two vectors, it's going to give me the area of the parallelogram defined by those two vectors. Okay, so that's why two forms are not just any 0-2 tensor. They're the special 0-2 tensors which when I give them two vectors, they're going to give me the area defined by those two, by the parallelogram defined by those two vectors. Okay, so I'm going to define something called the wedge product. So I'm going to define the wedge product of, let's say I've got my two basis 1 forms in the xy plane. So the wedge product of those two I'm going to define as the tensor product of dx dy minus dy tensor dx. Good. And this 0-2 tensor is precisely what I want. If I feed this 0-2 tensor two vectors, it's going to give me precisely the area up to a side. So let's just see how that works. Also, it's a good exercise to see how that works so we can get used to our notation. So let me feed this, feed that a vector v and a vector w, and I think I'm going to do this really the long way. Okay, so from its definition, this is going to be dx product dy acting on v on w minus dy minus dx acting on v and then from the definition of the tensor product, this is going to be v acting on v times dy acting on w minus dy acting on v times dx acting on w. And so that's going to be writing out vi. So it's going to be v dx acting on ei. And now this is the one form in the x direction. So when this acts on ei, this is going to give me 1 when I is equal to x and 0 when I is equal to y. Okay, so this is going to give me delta xi. So this is just going to pick out the x component of Vx. This whole thing is just going to be Vx. Similarly, that is going to give me Wy. That's going to give me Vy. And this is going to give me Wx. And this is nothing but, depending on how my vectors work out, this is nothing but plus or minus the area. So if I feed two vectors to this one form, that's precisely the object I wanted. It gives me the area up to a sign defined by those two vectors. Any questions? Right, so the sign just defines some orientation for us. So I could either define this as my area 1 form, sorry, area 2 form, or I could have defined that as my area 1 form. Depending on which one I choose, that defines a particular orientation for the two-dimensional plane. Okay, so we're going to take this as our area 1 form, and now we think of areas as not just a positive number, but the plus or minus sign gives us some orientation to that surface. What is up, what is down. Okay. Right, so we can generalize this definition of the area 2 form to give you the wedge product of any two arbitrary 1 forms, and that's going to give us what's called the 2 form. Okay, so I take two arbitrary 1 forms, and I'm going to create a new 2 form, which is a special 0-2 tensor, and I'm going to find the wedge product of two 1 forms in the same way as I defined the area 2 form. So that's going to be P times Q minus Q times P. Okay, and now we can go ahead and work out the components of this object. How am I doing for time machine?
You're doing well.
7 minutes to 11.
7 minutes to 11. Okay, well. Good. Okay, so I'll just probably finish with 2 forms. So let's look at the components. Let's see how this object acts on two arbitrary vectors. Okay, well, okay. So let me just mention. So it's not hard to see from this definition that this implies that the wedge product is antisymmetric. So the wedge product of Q, P and Q is equal to minus Q wedge P. Okay, that's just because if I exchange P and Q here, I'll exchange P and Q there, I'll exchange P and Q there, it'll be the same expression up to a minus sign. Everybody happy with that, or you want me to write it out in detail? Happy. Okay, so the wedge product, two forms are antisymmetric as opposed to the general 0-2 tensor, which is not necessarily antisymmetric. And let's see what the components of this object are. So I can write P wedge Q, and I can write these one forms in terms of my basis one forms. So that's going to be equal to P alpha x alpha. For some reason in my notes I've suddenly gone to space-time. Everything is pretty much the same. I have Q beta, P tilde x beta. And minus, so I put in there, and then I've got there, so there I've got Q alpha, dx alpha, sorry. P beta. Okay, now I can factorize and collect terms. So this is going to be P, okay, sorry, I've done this in a bad way. Yeah, okay, so let me just relabel that as, let me relabel these indices. Just relabeling alphas to betas and betas to alphas. So I can write this as P alpha Q beta, okay, good, times D tilde alpha times beta minus dx beta times dx alpha. Okay. And, sorry, this mess, which is not very legible, in the brackets is nothing but the components of that. So this is equal to P alpha Q beta dx alpha wedge dx beta. Okay, everybody happy? Sorry, I might have lost you. Any questions in case we missed? Alright, so I'm just going to introduce some shorthand notation. I'm going to write we're now going to have a basis for two forms, and we're going to write that as dx alpha wedge. Good. So I think I'll end with this. So as I've just said, this is equal to P alpha Q beta dx alpha wedge dx beta, and there are tildes there. Right. And I'm just going to rewrite this term twice. And now what I'm going to do, so I'm going to relabel the alphas to betas and relabel the betas to alphas. So that's P beta, Q alpha, beta. Okay, and we've already seen how this wedge product is antisymmetric. So I can take a minus sign and write that beta as an alpha, write that alpha as a beta, and then I can factorize out the dx alpha beta. So this will be equal to 1/2 times p alpha q beta minus p beta q alpha times dx alpha beta. And in terms of the notation I introduced, that is equal to P alpha Q beta dx alpha beta. Okay, but we've already seen that it's also equal to that. Okay, so what this wedge product does is it picks out the antisymmetric part. Okay, with a factor of 1/2. And I think okay, let me just do a little bit. How am I doing for time? Can I squeeze in a little bit more?
2 minutes.
Okay, so we're going to write the most general two form. I'm going to write it like this. And as I've just argued, that's going to be the same thing as the anti-symmetrization of the indices. Sorry, I'm shifting between space and time. Okay, so that's how we can write out the most general two form. So basically, another way you can think about a two form is it's a 0-2 tensor, which is completely antisymmetric in its cases. And we can just check that this object, these are actually the indices of this object. So let's just check that EI from EJ. Let's just check that that actually gives us AI, AJ. That's how we define the components. Okay, so that will be equal to 1/2 AIJ dxi dxj acting on E. Okay, sorry. Let's pull that K out. Acting on EK EL. Good. And then plugging in the definition of the wedge product, whenever dxi hits an EK, I'm going to get a delta IK. So plugging in the definition, you get 1/2 AIJ. So I get a delta IK, I get a delta JL, and then from the second term, I get a minus delta JK, delta IL. So carrying out that sum, I get 1/2 AK minus 1/2 LK. And the subject is antisymmetric in its indices, so that's equal to AKL. Okay, so that's the right way of writing in two form. When I feed it those two basis vectors, I get the KL components. Okay, that's how I define the components. Then I'll just end. Inspired by this, I'm going to define smooth side of the generalized quantum delta. Okay, so other than Robert. Okay, so I'll define I'm going to define. So this will be a determinant, and you get all the indices, right? Okay, and as we've just seen, this is equal to, I feed my basis form okay, so I think that's a good place to stop, and next time we'll learn more about 2 forms and 3 forms and about the Stokes system. So, thank you.